started. Good afternoon if you're from the West Coast, and good evening if you're on the East Coast. Welcome to the Potpourri session. My name is Nagi Naganathan. I'll be chairing this session. So this is a session where we have the mix of papers on verification, including RTL verification and also clock domain. So we have 4 papers in this session, 2 from Intel, 1 from Samsung, and 1 from Microchip. So the first one is from Intel Israel, titled A New Approach to Easily Resolve Hidden Timing Dangers of False Path Constraints on Clock Domain Crossing. The authors are Omri, Dassa, and Yossi Mirsky. It will be presented by Omri Dassa. He's a logic design team leader with 5 years of experience in the NIC industry, graduated with an honors degree in ECE from Hebrew University of Jerusalem. Omri, we can get started with the presentation.
My name is Omri Dassa. I'm going to present you a new approach to easily resolve the hidden timing dangers, false path constraints, and clock domain crossing. I'm going to co-present it with Yossi Mirsky. We are both from Intel Corporation, Jerusalem, Israel. First of all, an introduction for CDCs and false paths. We have to ask ourselves, are all CDCs are false paths? A common industry mistake is that they are, but that's not always true. Those CDC paths can generate some major silicon bugs we need to detect before moving on and generating the silicon. The previous solution was to do some manual work with the front end, and it was 100% the front-end responsibility to make sure that those paths are meeting the correct SKUs and the correct requirements, and we like to change that. So today we're going to talk about the CDC timing bugs, the previous solutions, and then I'm going to present our new solution. First of all, let's talk about clock domain crossing. We have the 2 flip-flops. The first is flip-flop 1, which clocked by clock 1, and the second is flip-flop 2, which clocked by clock 2. The clocks are asynchronous to each other. As you can see here, if at the rising edge of clock 2, the data that's sent to flip-flop number 2 will be changed, we might get a metastability issue at the output of flip-flop 2. This is something we like to avoid. The common ways to avoid this issue is using a simple 1-bit synchronizer. This is the solution if we like to synchronize only a single bit. The other solution is a bus synchronizer, which is a bit more complicated synchronization scheme. But we're gonna mainly focus about this bus synchronization scheme. Let's talk about static timing analysis. Static timing analysis is the tool that SD team uses in order to make sure that we meet the timing requirements. Let's take a look at the following example. Here we have 2 different MUXes, MUX number 0 and MUX number 1. They're both connected into the same select. So as you can see here, since they're both connected to the same select, we'll always get paths from in number 1 to in number 1, and paths from in number 0 to in number 0. The path from in number 0 to in number 1, it's not a functional path, and it can never happen. Yet, the STA mechanism might try to close timing requirements over this path, even though it's not a functional path. So we can define something that's called false path constraint, in order to let the STA tool know that this path is a false pass. We don't need to make sure that we close timing over it. The issue with false pass and CDCs is that CDCs are generally labeled as false pass. For example, at the bus synchronization scheme, you can see that the paths between flip-flop number 1 and flip-flop number 2 is considered a false path, since it's a synchronous path. And the other path that's considered as a false path is between the qualifier and the entrance of the synchronizer, the bus synchronization scheme. Both are async paths and considered as a false path. Let's see the impact of data skews when we try to send out several bits together, but using single bit synchronizers. If we do that, you can see here that we are trying to send some pattern, but we can assume that several of those single bit synchronizers will catch the signals at a different timing, since all of those paths are false paths. Therefore, the synthesis might implement them differently. We might get some delay over, let's say, bit number 0, bit number 2. Therefore, we'll generate those weird patterns, which is not what we sent, and we get out a different pattern from what we sent, meaning that this scheme is not good for synchronizing a bus, since it creates a skew between the data bits. So let's understand how the bus synchronization scheme works. So first, we're gonna send the data from flip-flop number 1 to flip-flop number 2. We do assume that the data is kept stable for minimum of at least 3 clock cycles of the receive clock domain. We're gonna, in parallel, send the qualifier to the synchronizer. Once we synchronize the qualifier and we generated the pulse from it, we will move the data from flip-flop 1 and sample it to flip-flop number 2. The data is sampled. You can see it here. Flip-flop number 1 send the data and make sure that it kept stable. We also send the qualifier at the same time. After a few cycles, we generated the select. Then we'll sample the data to flip-flop number 2. By that, we are making sure that the data that we are sampling to flip-flop number 2 is stable while we are sampling it, so we don't have any skews. We also don't have any metastability issues. One of the major issues with this bus synchronization method is that at very high speed and large designs, it might be an issue to send the data from flip-flop number 1 to flip-flop number 2, and from the qualifier to the synchronizer, since at large designs, those data can travel for several clock cycles. It will be hard to meet the data skew requirements in order to sample the correct data at the right time. Since the CDC paths are always considered as a false path at the beginning from the ESP team, we might get very high variation between the data bits themselves and the qualifier scheme. At past projects, we used some global constraint, for all the CDC paths, try to set a constraint of max delay of a single received clock cycle to all of the CDC paths, but at large designs, this constraint won't hold. If we don't make sure that the skew between the data and the qualifier is correct, we can have three different silicon bugs. The silicon bugs are not detectable in RTL simulation or at front-end CDC checks. So this is a major issue, and we have to make sure we detect those bugs in time, or we'll have a silicon bugs. The first bug here is the delay data bus bit. You can see here that when the data arrived in time, the qualifier is sent. Generally, we send the data, and then it takes some time for the data to get into E1, since this path might be long. The qualifier is also sent. After a few cycles, it got synced, and we sample the correct data. But let's assume that it takes the data some more extra time to arrive. You can see here that we set, some longer path to the data bits. Then when the qualifier arrives, select, the data hasn't arrived yet. So we might sample a different data than what we intended to, or if we do sample at the time that the data is changing, we might sample some metastable data. Another violation here is when we have some skew between one single bit from the data bit and all the other data bits. So you can see here, when all the data bits arrive together, we will sample what we intended to. But if one of the data bits will be delayed, we will sample a different value than what we intended to, and we might even get into a metastable issue with this single bit. So we have to make sure that all of the data bits arrive together and in time. The third issue is a delayed qualifier violation. Let's assume that all the data arrives together with the same skew, but if the qualifier will be late, we might change the data again before sampling the current data. So you can see here that we are trying to send some data from number 1. Then it arrived to E1 pretty shortly. The qualifier is sent with it, but it takes a lot of time for it to arrive to the select and sync together. So we might sample the wrong data or data that is just changing, taking the value at flip-flop number 2 wrong or metastable. If we do find those bugs, the solution is pretty simple. Let's assume that the bug that we found is the delayed bit bug. We can add buffers to all of the other bits of the bus. We can add buffers to the qualifier and align the skew between the qualifier and the data buses all together to make sure that our scheme works properly. So if we do detect those bugs, the solution is pretty simple. But the issue is that detection is not easy at all. So the previous detection strategies that we had is first by simulation. We can try detect these bugs using a gate level simulation. A gate level simulation with timing constraint might show us that the signals didn't synchronize correctly, or we got some metastable value. We can detect this issue. Another option is timing analysis. First, at previous project, we tried to set the max delay of a single RX clock to all of the async paths. And if it doesn't hold, we might have some issue and we need to check it. Another option is strictly naming convention for all of the CDC paths, the bus schemes. So we can try to go and detect those paths at the timing report from the SD team. Try to make sure that all the skews are managed correctly. The last option that we use is to generate some report from the CDC tool that analyze all the groups of paths that need to keep the skew requirements, and then try to manually review the reports from SD with the hints that we got from the CDC reports to make sure that the skews are held. So let's start to talk about a new solution. First of all, we have several assumptions regarding the new solution. Assumption number one is that large designs are usually divided at the RPA level into multiple partitions in order to let SD synthesize them more easily. At each partition level, there is no issue to solve the CDC paths requirement using the last constraint of making all of the paths meet the max constraint of a single RX clock cycle. So solving those paths at the partition level is negligible. And between partitions, the start point and the end point might be distant. So we do need to keep the skew requirements between partitions. Our goals here is to minimize the effort for the front-end team and remove the responsibility from the front-end team and take it to the back-end team. Yet, we don't like to add work for the back-end team. So we'll see how it all set up correctly. So in order to use our new solution, first of all, we take all of the CDC paths and group them according to the source partition and clock, and to the destination partition and clock. For example, here we have paths from partition X to partition Y. The paths at partition X are clocked by clock A, and are sent to partition Y at paths that clock by clock B. We'll group all of those paths together. Group all of those paths together in a single group. Another example for a group can be the paths from partition X B to partition Z clock C. All of those paths are grouped together as well. We can know that at the first group, we have two different bus synchronization schemes. So you might assume that each synchronization scheme need to make sure that the skill requirements are held within its own scheme. And we have two different schemes here, yet we group them together. And at the second group, we have even a single bit synchronizer, which is an actual real false pass. We don't need to make sure it meet any timing skew requirements, yet we group it together with a bus synchronization scheme that do need to meet the timing skew requirements. After we group all the paths together, we generate a report from the SD team for all of the data path delays of each path of the group. So you can see here that the report looks something like that. We have all the paths that start at the same partition, goes to the same destination partition, start with the same clock, and end at the same clock. And for each path, we have its own data path delay. Then we define the delay window. The delay window will be the timing window, the size of a single RX clock period. And we need to find the optimal window in time that contain the largest number of paths. So we'll do that by script. After we found this timing delay window, we'll mark all of the paths that are in this window as green dots. All of the paths that are outside of this window as red dots. As red dots. We'll set from this window, we'll set the mean delay as the beginning of the window, the max delay as the end of the window, and we'll give those constraints to the SD team. So we generated a constraint for the group. We do have some assumption here. We do assume that all of the paths from the same group usually travel similar distances. So they can all meet the same delay window. After we defined the group analysis and provided constraint to SD, we'll ask the SD team to perform a timing ECO iteration. Timing ECO, it's a stage where the SD tool try to meet all the constraints that we provided. So then we perform this group analysis constraint at timing ECO several times until we make sure that all of the paths enter to the delay window. So it looks something like this. At the first iteration, as we saw, we have several paths that are still outside of the delay window. But we made sure that the largest amount of paths as possible are in this window. The second iteration, you can see that first we chose a different window. We set a different constraint after this iteration. Also, you can see that the paths are more grouped together, and we have less paths that are outside of the delay window. Also, the paths that are outside of this delay window are starting to get closer to this delay window. After n iterations, we got to a point where all of the paths enter to this delay window. After we got to this point, we succeeded and we did what we wanted. We got all of the paths to meet the same skew requirement, and they are all grouped together and meeting a single Rx clock cycle period constraint. So the single bit synchronizer that didn't even needed to meet any of this constraint is now meeting them, even though it doesn't need to. And each mass synchronization scheme now meets the skew requirement since it enters this window. So the qualifier and the delta bits arrive together. So it doesn't matter if we have 10 different synchronization schemes here. Even if only one of them needs to meet the skew requirement, we'll constrain all of them together. We'll make sure that the one scheme that do need to meet this skew requirement, meeting it. So new solutions advantages. First of all, it's fully automated. At the front end, we're using a script. After we got the reports from SD, the grouping is done by script, and finding the correct constraint is done by script. Checking that the paths are in the delay window is also done by script. So it's no effort for the front end team. Our solution is bulletproof. Since we won't miss any skew requirement for any path, we give a global constraint to the group that cover all paths requirements. So we won't miss anything. Our method is fully automated, so there is no need for manual reviews here. so we won't have any new bugs from the manual reviews. And last, and the most important thing here, is that we don't even add effort to the SD team. Since timing ECOs are already part of the SD team cycles. If we sync our constraint giving with the SD team timing ECO cycles, we won't add any effort to the backend team. Do you have any questions?
Yeah, if you have any questions, yeah, you can either put in the chat or ask. Are there any questions? Hope everyone can hear.
I guess everything was clear.
I can hear.
Yeah. Maybe, it's a pretty interesting work. Let me ask a question. I mean, so are you able to handle, pretty big SOCs with this? I mean, the idea of, having everything upfront as part of the constraints is pretty good. I mean, that way, you are not trying to add any false path and things like that. So was it adding like a lot of effort to come up with this one in addition to developing the constraint? Because oftentimes, in a lot of places, STC is not taken care up front, it's done kind of towards the end and then always in a rush to get it done.
So you're asking if it was a lot of effort to generate the constraints or to apply them?
So the constraints were generated automatically by script. We only needed to get a report from SD. The report, as I saw just present the presentation, it's only fully report for all of the asynchronous stuff at the top level. Once we get this report, we can analyze it and generate a constraint from it using just a script. So there is no effort here. And after we generated the constraint, if we are providing them in time to the SD team, and then there is no additional effort for the SD team themselves, since they're already performing timing ECOs as part of the SD cycle.
So, but as to your point that you mentioned, the constraints won't be generated early in the project. This is something, it's automated, it's generated by a script automatically, but it's only something once you have a full release to the backend. That's the only point where you could generate these constraints, or, well, you could start earlier, but generate the final analysis of all the possible groupings and all the possible partitions and paths that go from one partition to another, with one clock to another. That's going to be done with your final release, and the script will automatically find all the possibilities and generate the appropriate constraints.
I think there's one more question in the chat, if you want to address that. Yeah.
Oh yeah, I mean, it's definitely true that there is over optimizing, over constraining here. But it was very minor. I mean, the impact was very minor. In the end, we took away a huge amount of effort and risk from the project, and the over constraining of the timing paths was just handled without any extra effort in the regular timing ECO cycles. There were a few violating paths here or there that were a little harder to close. So then we could review those. We did review those and decide whether they were true violations. Did they truly need to be over constrained or not? Other than a very small handful of exceptions, everything was just automatically, smoothly timed without any issues.
Okay, I think pretty much we are on time, I guess. If there are no other questions, I would like to thank you both. Pretty late night for you, I mean, past 1 a.m. So really appreciate it and great
Our
work.
pleasure. Thank you.
Yeah.
Thank you very much.
Thanks a lot.
I couldn't get the drum rolls, but you can see my hand.
Right.
Yeah, thank you.
Okay, thank you.
Okay. Yeah, okay, so now we will move on to the second presentation, which is the advanced fundamental verification for automotive system on a chip. The authors are from Samsung Electronics, and it will be presented by Jaein. She's a principal engineer with Samsung and involved with system level functional verification. So we can queue up the presentation. Broadcast.
Hello, my name is Jaein. Together with my colleagues Jieun Jeong, Namyoung Kim, Hongkyu Kim, Sungcheol Park of Samsung Electronics, and working with Sangjun Moon of Cadence Design Systems. We are going to talk today about advanced functional verification approaches for automotive SoC development. We will start by talking about the requirements of automotive system and corresponding verification challenges that will motivate this work. We organized the challenges in terms of completeness and efficiency. First, for completeness, we will explain the complex low-power design and how to ensure the verification quality. Next, for efficiency, we will explain the design features of self-diagnosis and recovery. And then we will present how to increase the verification efficiency. Finally, we will close this presentation with conclusion. Automotive applications that support ADAS are leading more of complex and larger system development. The number of integrated components are increased, especially for high-performance computing. The multiple cores, such as machine learning engines, CPU and GPU are required. They lead to a tremendous increase in a chip size. Automotive also requires completely isolated architecture for safety and security. To do that, low-power design has become more complicated, and associated usage scenarios can be exponentially increased. In addition, system reliability has become much more important in automotive. So corresponding self-diagnosis and recovery hardware scheme makes new verification challenges. From the beginning of complex SoC development, functional verification methodology has been evolved, and a lot of verification techniques are developed to increase the verification quality. However, they are still not enough to handle the explosive increase of chip size and complexity of automotive system. So we studied the limitation of existing verification approaches and present advanced approaches to deal with that verification challenges. Let's talk about ensuring verification completeness on low power design. This figure shows an example of automotive SoC low power design that has multiple voltage rails and power gating switches. SoC is partitioned into segmented power domains. It has analog components, and they need separate voltage supply. Many power rails are implemented for individual power control. Each power domain can have various power modes and power states, and associated possible state transitions are manifold. Verification engineers should verify that low power features such as power supply shutoff, power gating, retention, isolation, and dynamic voltage frequency scaling are properly implemented using power-aware simulation. The functional coverage is mainly used to check whether low power verification has been completed or not. If you look at this table, you can see that the example of power mode definition and the possibility of power gating cases and power status of each blocks. This kind of table can be translated as a single coverage group, and all conditions listed in the table can be defined as functional coverage bins. The previous approach is to implement the coverage model manually. However, there are too many bins and too many conditions to be considered, so manually implementing coverage models could lead to human errors. Also, any of missing coverage bins can hurt verification quality and may result in silicon malfunction. For the manual or ad hoc coverage model generation problems, we can get help from an advanced simulation tool. Cadence Xlium simulator supports auto coverage model generation by reading the UPF, the power intent file itself. With the LPS option of Cadence simulator, coverage model for the following power features like voltage supply, power switch, power state table, and control signals of isolation and retention are generated automatically. It helps to increase the power verification quality by checking whether all of power metrics described in the UPF are covered by verification. The figure in this page shows an example of coverage database analysis. After Power OS simulation, this IMC viewer tool read coverage DB and display the measured coverage like this. It shows the details of covered and uncovered bin for power signals like retention, isolation, and supply-net state, which are described in the UPF. This analysis tool helps to identify missing scenarios quickly and useful to confirm all power signals are covered. The tool is definitely useful to check the power signal itself. However, this approach is not enough to ensure the power verification completeness, because we cannot confirm if necessary power events such as simultaneous or sequential power events are verified with test scenarios. In the real usage power scenarios, most of power events happens with system-level operation. Therefore, we extended functional coverage bins to combine system-level power management events with a set of system operations. We are going to explain what kinds of system events or operations should be checked with power and how they modeled as coverage metrics, along with example coverage code. This is a sample code snippet that combines system reset and power state. In here, the possible power modes for system reset are defined as all on, usage 1, and usage n. This coverage model will confirm those three power modes are covered with the system reset events. Automotive SoC will have multiple system resets and segmented reset regions, and the operation of power mode state can be different for each reset event. So it is important to verify the reset assertion and deassertion behavior in all possible power mode state are working as expected. Interrupt signal may occur multiple power domains, hence interrupt handling also need to be checked with power features. This is sample cross-coverage code snippet for interrupt handling and power state transitions. If there is wrong isolation values in UPF, it can cause unexpected interrupts or system malfunction. As the coverage model checks the interrupt generation and handling over power mode transitions, any malfunction of interrupt or power transition errors can be detected. In addition, it will help to identify any missing system-level scenarios regarding to the interrupt handling and power transition use cases. We shared another reference coverage model for LPI handshaking. Before any power domain is turned off, power control system must ensure that there are no remaining transactions. LPI is used to check the idleness. If there is any missing LPI or the order of LPI is incorrect, the system may go malfunction. For example, system can be hanged during power up or power down, or IP operation is not working after power up due to the LPI issues. The sample code snippet closely checks the Q channel handshaking and the power state. It is recommended to cover all LPI interface in the system. Then you will find not only the missing LPI connections, but also the power control module errors. So far, we focused on the coverage metrics, and from now on, we are going to talk about assertions that enhance debug capabilities and efficiency of power verification. During the power-aware simulation, objects inside the shut-off domain are corrupted with generated unknown values. So we need X-propagation verification in power-aware simulation to identify possible X problems in the real silicon. However, the power-aware X-propagation simulation is very time-consuming and tedious for bug identification. So, using assertion help the verification engineer to easily find the X problems, and it enables faster power issue detection without waveform analysis. In this page, we have listed up the examples that can use the assertion checkers. As you can see, the signal values and signal conditions and the order of power events can be checked by assertion. For the practical help, among these, the isolation control assertion code will be provided in the next page. This is an example assertion code of describing the rules of isolation control. The isolation rules can be simply checked with this example code. The things to keep in mind is that this should be described all the isolation signals. Then it will help verification engineer to reduce debug time for any of isolation control issues. As we explained, we proposed the approaches to increase the number of coverage metrics and assertions for low power features. With the help of these approaches, we identified critical design errors during the pre-silicon verification and achieved a low power bug-free silicons. Here we categorized the types of bugs we found: wrong power sequence, isolation problems, LPI issues, power control module errors, and missing test scenarios. Now, we would like to move on to the next challenge, the verification efficiency. Automotive system has strong safety requirements and must guarantee system reliability at hardware level. It is important to check the hardware components before system activation or during the system operation. Whenever system is turned off, we should check if all components are under proper and safe state. And this test is post, as known as power on self-test. In addition, we must periodically check the system component while system is running. This test is called as IST, in-system test. This system self-diagnosis and recovery relies on BEAST. The target component can be memories and logics. As the memory size and the number of memories increase, the memory BEAST time increases and gets complicated. The situation is worse at logic BEAST because logic BEAST is implemented with built on scan chain. The scan chain is only visible at NAND list, so we cannot verify it at RTL level. So this results in longer simulation time. This figure shows an example of BIST execution sequence to be verified at system level. When system is powered on, toast will be performed with dedicated code ROM. After that, system starts normal operation with monitoring IPs, that is checking any temperature or voltage drop. If something is detected, or just after a certain period of time, system will enter idle state and execute IST to check the system. This system operation and IST operation will be repeated until system is powered off. The BIST operation must be checked by SoC level verification before the silicon, but it is almost impossible to cover by simulation due to the size and time. A conventional method of reducing simulation TAT is to cut down the complete BIST pattern and usage scenario. Here you can see the example BIST patterns and difference between full pattern and partial pattern. Full pattern, which is located in left side, covers all of memory instances, but partial pattern located in the right side only cover one memory instance of each BIST controller. Using the partial pattern, we can possibly run simulation to check the BIST controller operations, but this approach can miss design errors, such as misconnection between memory and BIST logic. In addition to the BIST pattern, scenario sequence also can be cut down. Instead of running full sequence, test is divided according to the system operation mode. Using this way, we can confirm individual sequence by simulation, but we cannot cover the real usage scenarios, and we may possibly ignore design errors of system operation mode changes. As explained, conventional cut-down approach only checks the functional feasibility, but limits verification coverage. So we need to find another way to accelerate the simulation. Using emulator can be a good solution. We can map the design into hardware platform and utilize the full hardware speed. But to use emulator, we must resolve the following emulator hurdles: the limitation of hardware capacity, redundant design analysis flow, and low debugging capability. The simplest way of reducing emulator capacity is to replace unnecessary blocks other than targets with black box. The figure shows the conventional emulation test bench and how the design is mapping to the hardware emulator. Target design is synthesized by emulator's design analysis flow before loaded in hardware emulator. We can verify the memory-based operation using this conventional emulation test bench, but it is not suitable for logic-based verification because logic-based is implemented in NAND list consumes more hardware area than RTL, and we need more budget for logic-based as well as real usage scenario verification. Another problem is that even if we use the NAND list, emulator try to synthesize the NAND list to mapping it into the hardware platform. This flow of emulator design analysis can make misinterpretation between the actual NAND list and the emulator image. To overcome these hurdles, we propose a new test bench architecture for the logic-based verification and real usage scenarios. Here you can see the proposed emulation test bench diagram. We reconfigure the DUT by mixing the RTL, black box, and netlist. And the reconfigured DUT is mapped into hardware as a single platform. We try to minimize the netlist portion to limit only logic-based design, and we configure most necessary parts as RTL to save hardware capacity and to reuse existing software codes. Especially for the netlist, we skipped the design analysis flow and mapped the original netlist as it is by emulator support. As we don't need to resynthesize the netlist portion, we could save compilation time and unnecessary iterations. With the help of this test bench, we can verify full pattern list for both memory and logic. It enables to create and run the real usage scenarios as well. When we create and run usage scenarios, we got a lot of debugging help from emulator technology. The emulator support to probe the RTL signal during the runtime without any compilation. It was very useful to merge and debug list sequence during real usage verification. We could verify the system operation mode over all expected BIST operation at pre-silicon verification page. Here is the summary of BIST verification results. It shows the results of comparing the BIST pattern coverage and runtime between simulation and emulation. For the post, the coverage of simulation pattern ROM is only 10%, and it takes around 3 days. Compared to that, in emulation, 100% coverage ROM can be used, and emulation takes only 2 hours. For the memory BIST pattern coverage is 26%, and simulation time consumed around 6 days. However, in emulation, 100% coverage vector completed within 5 hours. For the logic BIST, simulation was failed to complete for one pattern. However, for 16K random pattern logic BIST, emulation test consumed around 48 hours. The conclusions. We improved low power verification quality by auto-generated coverage metrics and assertions and combining them with the system operating mode. We proposed new emulation test bench that configured with netlist, RTL, and black box for efficient use of emulator. These approaches enable us identifying corner case bugs and design issues that were remained undetectable during pre-silicon verification phase. We could achieve a one-time correct silicon development for a billion-gate automotive SoC. Thank you for your attention and listening. Please let me know if you have any questions.
Yeah, thank you. If you have any questions, feel free to ask or put it in the chat. Is everyone able to hear, or? Yeah, maybe let me ask a question. You mentioned about this post where you check for safety. I was curious. So, what do you check for safety? Yeah, Jaein, can you hear me?
Oh, yes.
Sorry for not enabling the camera because my office is not allowed to enable the camera. So for the
Yeah.
safety
Yeah.
is the feature of the feature of the automotive system, but I'm focusing on the complexity and then the efficiency of the automotive system due to the safety feature. So to isolate the safety system, the low power system is more complicated. So I focused on the low power design, low power verification completeness. So that's why I mentioned the safety and security in my paper.
Okay. Okay. Yeah, somehow I misunderstood as you were checking for certain things in that mode, but that is not the case, looks like, right?
Yes.
Yeah. Okay. Are there any questions? Yeah, also, I forgot to mention earlier, I mean, please vote for the presentation also. And if there are no other questions, then I would like to thank you for a great work. I mean, looks like you have covered a gamut of things with the verification, I mean, and emulation. So thanks for your presentation and great paper.
Thank you for the comments and thanks for the giving chance to involve this DVCon. Thank you.
Thank you. Okay, moving along, the third paper, the third presentation is titled Leaping Left, Seamless IP to SoC Handoff. The authors are from Intel. It will be presented by Swetha, Thiagarajan, and Rashika. Let me first introduce Swetha. I mean, she has over 15 years of experience in semiconductors, graphics display, and SoC. She's a transformative leader with strong organizational skills while constantly looking to challenge status quo. She has a proven track record for architecting scalable tooling solutions. Her career has spanned technical and managerial roles in design validation for embedded products, graphics, and SoCs. She's currently a technical advisor and chief of staff at Intel. And our co-presenter Rashika has 4 years of experience in SoC design. So over to you, Swetha. We can start the video.
Hello, and welcome to this presentation on Leaping Left, Seamless IP to SoC Handoff. I am Swetha Thiagarajan, Technical Advisor and Chief of Staff at Intel, and together with my colleague Rashika, we will walk you through the challenges, tools, methodologies, and efficiency improvements driving IP to SoC handoff. I would also like to take the opportunity to thank our co-authors, Hiran and Sangeivi, for their contributions to the project and the paper. Through this presentation, we will reintroduce a problem that is common across the industry, IP to SoC handoff, how we intended to solve this for graphics IPs, challenges we faced, and results from a latest product where we deployed the solution. We will then round up the presentation with conclusions and next steps, and also set the stage for questions. The cycle of packaging an IP and integrating the same into an SoC took an average of 4 weeks per IP drop. This was mainly due to a lack of standard packaging flows and efficient methodologies to check IP design quality. Further, an abundance of hacks and undocumented workarounds compromised the quality of the IP drops per integration. Additionally, there weren't any efficient methodologies to check IP design quality against industry and SOC standards. This required substantial manual effort to generate IP packages and thorough testing at IPs before making an SOC delivery. A typical product lifecycle of PLC defines the lifecycle of a product all the way from concept definition through execution and post-production. The milestones and stringent timelines for these drops are set by a governance body and SOC. With that in mind, all graphics IPs being just in time introduces a whole new set of challenges. For a new project, version 1 being the first drop to a particular SOC, packaging the IP would by itself take a week to assemble and deliver. The delivered milestone drop then goes through its own set of backend checks and would take at least 3 weeks to integrate into SOC. We are not yet talking about a boot sequence test passing. The time to package and integrate to SOC shortens as the IP matures, but it isn't without its own challenges. SOC reports integration issues, IP delivers hotfixes or spins a pre or post version X drop. The fixes and hacks sometimes don't get propagated into the IP repos, or they just go undocumented. And the same bug would reoccur in the next drop, or sometimes even the next product. At one point, we had an IP that delivered 39 drops total to an SOC for a single product. This created a huge overhead for the IPs and the SOCs who are integrating them. Our bottom line was to develop a mechanism to package an IP through a continuous integration, always alive system. This, of course, required a refined tool, flow, and a methodology, and with the goal of reduced time to market. We went through at least 2 iterations of packaging flows. The legacy IP packaging solution had noticeable shortcomings that resulted in multiple integration bugs and hotfixes. Our initial solution was a diversified utility that completely transformed an IP to an SOC-based model. While this provided extensive customization hooks, lack of centralization forced each IP to maintain their own copy of a flow that was heavily tied to the TFM and the environment. This led to noticeable shortcomings, which included the need for an IP and the SOC's build system to be aligned, as well as requiring the tool versions between the two to be converged. This apparent lack of portability eventually resulted in multiple integration bugs and hotfixes. Its successor addressed many of these shortcomings. With the improved package structure, fewer issues were seen at discrete and integrated SOCs, resulting in better integration TAT. IPs didn't need to maintain individual copies of the flow anymore because of better centralization. However, tool customization across soft IPs and hard IPs became expensive. Different approaches to CTEX, memories, DFT, and validation collateral delivery are some of the areas where IP's customization come into the picture. This solution also assumed that SOC would be using certain TFMs, which rendered unfeasible when SOC moved to a different TFM in the most recent project. Additionally, the lack of a good quality assurance tool led to several front-end integration issues to go unnoticed and being caught only at SOC. While SOC did have a quality assurance tool which can be used to run several static checks on the generated package by passing through log files, we weren't able to efficiently utilize it due to IP versus SOC environment dissimilarities. And some of these were non-applicable checks to our graphics IPs. We actively studied how various external vendors developed their IPs and allied also internally to align on the IP to SOC guidelines. A successful IP delivery is measured by the ease of integration into an SOC along with small time to market. We quickly realized what was needed. The continuous integration model to package the IP while being both TFM agnostic and scalable across SoCs. The overall framework should be consistent across graphics IPs with customization hooks and switches available to help meet unique SoC delivery requirements. The goal was to keep the mechanism environment agnostic and be used to deliver to any SoC, irrespective of its TFM. We understand the speedy delivery of IP comes with its own set of limitations. To ensure that the milestone drops meet quality prior to handoff and is LRM compliant, quality assurance would need to be added to ensure that the package is self-contained and compiled standalone on a clean RTL only and an RTL plus val file list. This qualified IP package should then undergo rigorous checking mechanisms so it fully meets the IP to SoC handoff exit criteria. Enter export IP, which packages the IP and runs quality assurance on the package. Furthermore, we developed Orion, which is a robust quality checker infrastructure. I will now hand this presentation over to Rashika, who will walk you through the architecture of the tools and the flows that we developed, challenges during deployment, as well as the results.
Thank you, Swetha, for setting up the stage. Hello, everyone. I'm Rashika, an SoC design engineer at Intel, and we will now dive into the architecture of this novel packaging tool, Export IP, which is always alive as has its own built-in qualification mechanism. While architecting Export IP, our focus was to develop a robust IP packaging and qualification framework that is TFM agnostic, so that we don't have to start over each time SoC changed TFMs, as we had to do in the past. We combined the strengths of our all previous solutions while addressing their shortcomings. There are three primary stages to packaging an IP: create IP data, generate the package, and run standalone QA. To create IP data, Export IP leverages built-in APIs from IP's native build system. The second stage then takes this data dump, converts them into industry standard file lists that can be plugged into any downstream compiler. IPs can customize how the collateral gets packaged, depending on the SoC requirements. We even introduced additional knobs so that the same tool can be leveraged to build a structural design package. This allowed us a consistent infrastructure across front-end simulation, emulation, as well as SoC and SD handoff. This allowed consistency across all downstream consumers of the package, resulting in fewer bug escapes. To ensure that the quality of the generated package, a third stage, qualification assurance, was added. The qualification flow is maintained through a combination of central and local makefiles. While central makefile is responsible for overall QA environment and supporting new checks, IP makefiles maintained commands specific to those IPs to launch these checks. This scalable QA setup allows IPs to effortlessly enable or disable any test based on IP readiness and their commitment to SoC. As of now, Spyglass designed a compilation on RTL file list to ensure basic synthesizability of IP, and a multi-vendor standalone simulation on RTL and val file list combined to ensure strong LRM compliance is supported. Moving on to the inner workings of Orion QC. So the finally generated package, which is qualified, is now passed through a quality checker, which can be configured as per the drop requirements defined by the IP contract. The tool runs on the generated package to ensure that the front-end, back-end, and SIP compliance checks are met, and it meticulously passes through the package to guarantee that it meets the PLC milestone requirements. This Orion tool takes the package, configuration files, and a set of checklist items as inputs. It has a top-level wrapper that helps IPs toggle between underlying scripts. It kicks off additional checks that weren't a part of IP environment but are required by SOC. It checks for file presence, verifies that final report of each underlying check, collate all the log files and reports, and also uses an automated email generator to send out the release notes and the results to the IP team. We categorize the checks in these main categories: front-end, back-end, SIP compliance, emulation, file presence, and IP-specific custom checks. Front-end checks ensure basic VCS elaboration. They flag illegal macro definition and macro usage, thereby ensuring code compliance. Back-end checks check for latches, undriven pins, and CTIC compliance. SIP checks verify usage of global or vendor-specific macros. Emulation, on the other hand, checks that the package is emulation-friendly on various platforms such as Zebu, Veloce, etc. File existing checks ensure that the IP package satisfies IP to SOC deliverables. And last but not the least, custom checks can also be added for IPs to meet unique requirements for that particular IP. Let's discuss some challenges and solutions. Deployment of a new packaging tool and a quality checker came with its own fair share of challenges. This slide discusses our main challenges and devised solutions. Packaging large graphics IPs with over 150,000 files, each created severe compute and runtime cost. We countered this by implementing most of the package building and validation on a local or a temp disk to avoid system crash. Another challenge was to reduce high turnaround times for a qualified package. We identified that the unnecessary elaboration dependencies and sequential execution of the qualification checks were to blame for high turnaround times. The smart build infrastructure and QA parallelization resulted in substantial improvement in this area. During the early execution phase, SOCs are focused on the RTL bring-up. Having validation collateral dependencies hinders with the model bring-up. The lack of RTL and val separation also hindered our ability to implement full spectrum of QA checks in the initial phases. Necessary changes were made at IP top level to separate RTL and val libraries. Customizations are great when it comes to give IPs the flexibility to cater to specific SOC or milestone requirements. However, each customization brings us one step further away from streamlining libraries and features across the IPs. To counter this, we identified all the active features which are common across IPs and consolidated them in a version-controlled central release area. To discuss improvements, here we show each of our solutions resulted in significant turnaround time improvements. Implementing temp feature and parallelizing the QA improved display turnaround time by 59%. Something to note here is that media and GPU IPs clearly have more opportunities for additional parallelization in the future. The second table shows how smart build can substantially reduce turnaround times by eliminating dependencies. Again, GPU IP didn't see much improvement here because it has dependencies on a compiler-generated header file, which cannot be eliminated without substantially making test bench changes. Lastly, we can see the consolidated turnaround time improvement because of all the enhancements combined. As expected, GPU turnaround time saw least overall improvement because of lesser scope of parallelization and compiler dependencies, whereas display and media delivered promising results. Moving on to results, due to its robust and configurable architecture, Export IP and Orion QC were seamlessly adopted by all Intel graphic IPs. This entire solution took our team 3.5 man-months to develop, test, and deploy. To break down the time frame, it took 1.5 months to develop the Export IP framework, 1 month to develop Orion QC, and another 1 month of exhaustive testing and integrating the solution into the display IP. In addition to the higher quality drops, Display was able to use the same infrastructure to deliver to different SoCs with varying requirements. In prior programs, SoC integrations of display IP would typically take 2 to 3 weeks. With export IP and Orion quality checker, this was reduced to just 3 days, 1 day to build and deliver the package, and 2 days to successfully integrate it at SoC. This also allowed the graphics IP to auto-integrate into their SoC die through a continuous integration framework and observe a 50% headcount reduction from integration team. This table provides a comparison in IP packaging turnaround time and front-end SoC integration turnaround time between previous program and export IP implementation for GPU, media, and display IPs. We can see a significantly lower packaging and integration turnaround time with this novel approach. Previously, quality checks were manual and would take up to a week to complete. With Orion, we would get results back in approximately 3 hours. The number of unnecessary revisions due to poor quality drops was reduced to nearly 0. And the integration bugs filed by SoC was just under 5 throughout the entire program. This extensible framework was seamlessly adopted by additional IPs for next generation programs. To conclude, front-end integration turnaround time decreased from an IP delivery perspective while also reducing the integration bugs, significantly shifting left to the IP owning the responsibility for quality milestone drops. Export IP and Orion Quality Checker both delivered results immediately upon deployment. From an IP delivery perspective, both front-end integration turnaround time as well as integration bugs were significantly decreased. This results in a major left shift as it lessens the burden on IP SoC integration and allows IPs to own the responsibility for delivering quality drops. This approach resolved past issues on TFM dependencies, environment, configurability. The QA approach has also even been utilized across other IPs outside graphics. For future projects, we will continue to focus on the quality of IP delivery. Our roadmap strives to enhance the features to continuously surpass established industry standards. This includes a reference test bench delivery for boot sequences, addition of a secondary simulator to increase our IP's LRM compliance, and mock SoC to ensure that the transformed IP package is comprehensive and meets PLC standards. For Orion Quality Checker, support for an online reporting dashboard and indicators are being implemented. As we work through the challenges of IP's complexity, improving the performance to reduce turnaround time continues to have a strong hold on our roadmap. Thank you for your time, and we are now ready for questions.
Yeah, thank you. Yeah, are there any questions? Are there any questions? Yeah. Okay, maybe I'll make a comment on that question. I empathize with you on the IP, the SoC integration, because I used to be involved with that. You mentioned about, the CDC abstract and things like that. So I was just curious, what about, the constraints in UPF? Because oftentimes when we integrate the IP, right, I mean, that is one of the major issues, because the IP level constraints probably could not be easily ported to the SoC. and same with UPF.
So let me take this, Rashika, you can add more details. So we've actually, as we were delivering all of these collateral, right, we've delivered our UPF as well as provided the constraints, and then the SOC actually uses those constraints to up-level it for their integration work into SOC. So we deliver all of the reports and the collateral along with the drop with the IP delivery. Rashika, do you want to add anything?
No, I think as a part of the IP delivery from IP end, we basically just check for UPF file presence and make sure all the collaterals are present. But the other half of this quality checker that we are working on CDF, that takes care of checking out if UPF constraints are actually matching SOC requirements. So that's a complementary tool to this, which basically works on behalf of SOCs. When they check for IP deliveries, they take care of UPF constraints and requirements and make sure that we run something called as UPF inspect and other tools to ensure that constraints are all right.
Yeah, thank you. I think there are a couple of questions in the chat. You may want to address them. Yeah.
Right. So what CI platform we use this tooling called Gatekeeper. So it's it uses Git in the background, and that's what we use. And this is, of course, it's an always alive platform. So it's something that we check into Git, and then that basically makes sure that all of the checks and balances are run, Git level tests are run, and things like that in the background. And okay, what's the next question? So we actually, I have to mention that we don't have analog blocks. So I really don't have an answer to that, especially with the graphics IPs. Any more questions?
Any more questions?
Yeah.
I just want to make one comment. I mean, though we have all these checks and everything, right? A lot of times these are dictated by the customer, right?
Correct.
So you end up giving something, the SOC to the customer with an IP which is not fully qualified. Then that is the biggest challenge. But is this all internal, or if you are dealing with an external customer, that is a challenge.
So what we did do was that we actually looked at what our external customer, basically what others outside of Intel do, and we tried to see how we can adapt some of those things. For example, right, some of these obviously, how you deal with an off-the-shelf IP is very different from how you actually deal with a just-in-time IP. And over here, all of our graphics IPs are just-in-time. So basically, it requires a lot more customization as compared to, say, you have some Synopsys IP that's sitting, and they've verified this on multiple OSs. They've verified it with multiple versions of the tools, right? And they're able to deliver it. But it doesn't work that way when you're just in time, right? So that's the kind of challenge that we face when we're delivering it to our internal SOCs. Yeah.
Yeah, thank you. Are there other questions? Yeah. So they say that IP, actually stands for intense pain. So, we all can, feel that pain, So,
yes, absolutely.
Yeah. and I'm also curious, you're saying left shift, you are left shifting to the IP team. Hopefully that is not right shifting their schedule.
So that's another thing. Yes, absolutely.
Yeah.
That's very true. And it's one of the things that we actually bake into our system today, because what has happened is that as now, either we as an IP actually take care of all of the checks and balances before we deliver to SOC, or SOC is actually catching these issues and they're delivering it, and they're basically feeding it back to us, right? And when we went and looked at this, we realized that the kind of back and forth that happens with SOC is so much more overhead for both IP and SOC that it made sense to actually bake into the schedule a little bit more time to do the checks and balances ourselves. It's just ROI, right? Is there more ROI with us doing an IP the work, or having SOC catch these issues for us? So, yeah. But you're absolutely right. There is definitely some schedule impact, but you bake it into the schedule.
Yeah, and that's always a pushback, right? I mean, so
Correct.
that is the challenge. Yeah.
Yes.
Yeah. So are there any more questions? We still have 5 minutes time, so that's why I was asking for.
Yeah, we started early too. So.
Yeah, right. Yeah, thank you very much. Hopefully true to the name of Orion, the most visible constellation. I'm sure this tool is most visible within the company, and making IP integration smoother. Thank you very much to both you and Rashika on a great presentation. And
thank you very much.
Please, vote for the presentation. So, yeah, thank you. Yeah, thank you. Okay, I think we have the last presentation, which is it a software bug or is it a hardware bug? Kind of interesting one, depending on whom you ask, whether you ask a software guy or a hardware guy. The authors are from Microchip, and it will be presented by Horace Chan. He has over 20 years of experience in verification. He specialized in hardware and software co-verification, porting existing test bench to emulation. His paper on emulation has won the DVCon 2019 Best Paper Award, second place. Horace Chan. You can start the presentation.
How can I start it?
Yeah, no, so I'm asking the conference catalyst workers. You can queue up the presentation. Yeah.
Good afternoon. Welcome to my presentation titled, Is it a software bug? Is it a hardware bug? This paper started off as a training for the new members in my emulation team. It documents the most common emulation bugs we see in our day-to-day work and how to deal with them. Since I already wrote the content, might as well turn it into a DVCon paper and share it with you all. Hope you will find something interesting in the next 30 minutes. This is today's agenda. First, as usual, we will have an introduction. We will talk a little bit about the problems every emulation engineer faces every day. Bugs, lots of bugs. But where is the bugs? Then I will go over some techniques that we have developed to help us find the bugs. Bugs are everywhere. In the software, in the emulation builds, and of course, in the RTL too. I will also share some tips on post-silicon debug using the emulation platform. At last, we will have the conclusion as usual, and then it's time to answer your questions. Shift left. I am sure you have seen this picture many times, and you must be bored of it. So, I am not going to preach to the choir. If you're already here, you don't need me to convince you the benefit of emulation testing. One side effect of shifting left is we see more bugs. The more you shift left, the less stable the RTL. Sometimes the emulation tests even see the RTL bugs before the simulation. Well, the emulator runs a lot faster than the simulator. In an ideal world, when the hardware designers and the software developers follow the best practice religiously, we will see a lot less bugs. I highly recommend this paper from DVCon 2020. What your software team would like the RTL team to know. Most of the bugs we come across every day in emulation can be easily avoided. Yet, we still see those bugs again and again. Most of it may sound like common sense to you, but when the schedule is tight, documentation is the first corner to cut, and communication between the software team and the hardware team breaks down. It is no one's fault. It is just a fact of life and job creation for the emulation engineers. Emulation tests the integration of software and hardware. It covers hardware features that are hard to simulate, like the test that takes way too long to run in simulator. Emulation is supposed to catch system bugs. If you keep seeing software bugs that should be caught by unit tests, or RTL bugs that should be caught by simulations, you have a much deeper problem. Talk to your verification manager and your software testing manager. Don't waste the precious time of your emulator on bugs that should not be your problem in the first place. The hardware-software interface is where software meets the hardware. Whether a problem is a bug or a feature, sometimes it's hard to say. At the end of the day, as long as the software works with the hardware, deliver the system feature as specified. Who has to fix their code is not that important. The software team and the hardware team live in two totally different worlds. Each of them has different workflow and debug tools. And sometimes they blame each other when problems arise. It is not my fault, it is your fault. You should fix the code. When a test fails in emulation, it is up to the emulation engineer to triage where the problem locates. Is it a software bug? Is it a hardware bug? Or is it an undocumented feature? Emulation engineer is a full stack expert who can debug the software and the RTL equally well. Who knows how to use GDB and the waveform viewer. A multilingual who speaks in both C++ and System Verilog, or any other programming languages used in the design. When the software team disagrees with the hardware team on the implementation, the emulation team is a judge who presents the evidence to the system architect that makes the final call. Although I call it a software bug, because it is a software team who has to fix the code, it is really undocumented change of the hardware-software interface that the software team is not aware of. Sometimes the verification test bench and the test cases are the golden reference, the real design document, not the Word doc that never get updates. One of the common problems we see is the magic bit. When the hardware designer has to patch something in the RTL, no one in the software team knows what is the correct register value to make the hardware work. Therefore, the software fails. We have developed some scripts to automate the comparison of the register dumps from the software test running in the emulation and from the simulation log. The script itself is nothing fancy. I believe each company has their flow to generate C++ header files, the RTL files of the register blocks, and the UVM register files from the IP exec register definitions. It is just some tedious work to make them all line up with each other and report mismatch. The next problem is very similar to the last one. The designer changed the configuration sequence on how to set up the RTL without telling the software team. Although the register values are the same, but the execution order is different. So it doesn't work. We cannot rely on comparing the software log with the simulation log to catch mismatches in the configuration sequence, as the register access in the test bench is very different than the register access in the software. We have developed a way to run a section of the UVM config sequence from the test bench in lieu of the software config function in the emulation box, and vice versa. We can run a section of the software code in the test bench. Please see my DVCon 2019 paper, How to Test the Whole Firmware Software When the RTL Cannot Feed the Emulator, for the implementation details. That paper won the DVCon Best Paper Award 2nd place. Please vote for my paper this year. Thank you. We, the emulation engineers, tend to assume the bugs is in either the software side or the hardware side. But sometimes it is our fault. We pick the wrong RTL release when we compile the emulation build, or we pick an incompatible software version to run the test. In an ideal world, where the software and the hardware code are controlled by the same release management systems, all the new releases and updates are communicated to everyone in the project, we won't see this problem. Unfortunately, the reality is a lot messier. Manually checking all the release notes from the RTL, the test bench, the software, and the emulation environment are aligned properly is very time-consuming and prone to human error. We automated checking of all the releases by adding a read-only revision ID register in each IP block. The revision ID is updated by keyword substitutions in subversion in each release. We also implement the equivalent of keyword substitutions in Git using smudge and clean filters. Please see the code in the paper for implementation details. After we ruled out all the possibility of software and build problems, the only logical conclusion is a hardware bug. Armed with the undisputable truth of the waveform and system Verilog assertions, we can enlist the help of the designers and the verifiers to look at the problem. Many emulation engineers have verification background, so we feel like home with waveforms and assertions. Thanks to the speed of emulation, we can dump a lot more waveform a lot faster. It is slightly different use model compared to dumping the waveform in simulation. There are two types of emulation platforms, the FPGA based and the custom processor based, namely Protium and Palladium. Protium runs 10 times faster and costs less than half of the price, but it takes 2 days to recompile a build to add some signals to the waveform, and there's a limit of the numbers of the signals it can probe. On the other hand, the Palladium has no such limitations. We can dump waveform just like the simulator, and it even takes less time to compile. To me, Palladium is like a very expensive simulator. It can do anything the simulator can do, but it runs 1,000 times faster. We always compile the Protium build with some signal probes at key interface of the design. the probes should focus on the internal states of the device, which is not observable by software, such as the FIFO field level, the blood pressure tokens, timestamps of the packets, etc., etc. The waveform capture is triggered on interrupts or error conditions. With luck, those signals will give us good insights into what's wrong with the RTL. Due to the high price tag, Palladium is always a limited resource. It is reserved to run initial bring-up and debug complicated problems. Interactive debug to explore different configurations and traffic stimulus provide most value in understanding the complexity between the software and the hardware. The key is to shorten the debug turnaround time. Don't waste your time recompile the test case when you are on the box. Make your test case take command line arguments to configure the test. It is even better if the test case supports an interactive debug prompt. Let user change the configuration on the fly. Pause the test case at any test stage and loop over the error conditions on demand. It may take more time to build a test case support those debug features, but it will save you more time and efforts in the long run. Once the error stimulus is isolated, we can pass it on to the verification team to reproduce the bug in the test bench. Fix should arrive soon. When the chip comes back from the fab and the software is running on the silicon, very often the emulation environment is left to rot. Changes are made to the software test cases, and it no longer runs on emulation. One day, a corner case bug hits the fan. Once again, the emulation team is called into action to triage whether it is a software bug or a hardware bug. It will take a few days to clean up the software test case to make it run on emulation again. When the customers are waiting for an answer, the executives want a status report every 2 hours. Believe me, those 3 days are not fun. It is better to spend the same 3 days before this bug shows up. Keep the emulation environment always up to date. You may have to put in some address filters to block register accesses to the analog blocks. Make the timeout counters programmable, since the silicon runs a lot faster than the emulations. The key is to run the same software binary on the silicon and the emulation platform without recompile. Nothing is really hard if you plan ahead of time. If the problem can be reproduced in emulations, it is a digital problem. Just follow the previous steps to root cause the issue. If the problem is not reproducible, it is very likely an analog, timing, or yield problem. This flowchart recaps my presentations. When a test fails in emulations, if there are mismatches in the register dump or the config sequence, it is a software bug. If the RTL release mismatches, it is a build bug. Everything else is a RTL bug, and you just have to reproduce the problem in simulations to get it fixed. When a test failed in the silicon, if we can reproduce it in emulations, just follow the same steps to debug. If not, it is someone else's problem. In the past, before we have the automated tools, it used to take half a day to debug a mundane problem by hand. Now, it only takes 30 minutes. The tool can even pinpoint which check-in breaks the test, file a Jira test ticket with all the debug information, and email the guilty person to fix the bug. But the hard bugs are still hard to debug. The automated debug tools free up valuable time of the emulation engineers to work on the hard bugs, instead of babysitting the mundane issues again and again. It is hard to quantify the amount of time saved with the debug techniques presented in this paper, since debugging is always more of an art than science. This paper lays down a systematic approach to debug software and hardware issues in emulation. Hope you will find something useful, and please vote for me. The end.
Yeah, I think that, thank you. Yeah, I think that there is a question in the chat. You may want to.
Hello? Can you hear me?
Yeah. Yes. Yeah, there is a question in the chat.
Okay, so the question is, for analog IP, the register definitions must be flexible until very close to tape out. This means that register sequence used in emulation will need to be adjusted to match the update register map with each analog IP dropped to the emulation team. Do you have any suggestions that follow updates could be used so that the software is updated automatically? Okay, we actually have this problem. Even though we are not a analog IP, we are digital IP, the register just keep changing. Like it's just a fact of life. Register will change until the very end. So one thing like I like to stress is you have to automate your like register flow. Whether you use your internal tool or you use IP exec, you have to have all the header files, your test case, whether it's C test case or UVM test case. You cannot use any hardcode values of any address. You have to use a pre-generated offset address, offset defined files. As long as those pieces are always aligned, it is just a matter of revision control exercise. If you check out the right version of software with the right version of hardware, it should just work. So yeah, that is kind of my my suggestions. Don't hardcode anything. Okay, any other questions? Anyone still around?
There is, yeah, no, there is one more. Do you want to take that?
Okay, PSS. You know what? I'm actually the very first DVCon that used to have a PSS competition, annual PSS competition. I'm the very first champion of that competition. Oh, sorry, DVCon is at that actually. I tried to introduce PSS to my team. I set everything up. The problem is I could not find people to actually use it. The software team, they stick with their C code. The verification team, they stick with their UVM code. No one wants to learn the new things. If somehow we find some way that to force them to use it, I'm happy to, but I could not overcome the sheer momentum of how everyone do their things. Yeah, it was definitely helpful, but until people actually want to learn it, there's nothing, as an emulation guy, there's nothing I could do.
But if the sequence keeps changing, right? In other words, the sequence to do something keeps changing.
Yeah.
Tell them they need to automate it, right? You need to automate it. When they give you a new sequence with a new drop, you have to automatically fix your C code.
Yes and no. They'd rather create some fancy Excel spreadsheet to deal with it than use PSS.
That's not making sense to me.
I know. I'm preaching to the choir in this conference.
Okay.
Yeah, we have a way to deal with it. We don't do it by hand, but still, like from my perspective, I think PSS is way better. As long as they're willing to learn the syntax.
Okay, I think we can make a threat here. If nobody else asks another question, we can keep talking about this.
Sure, yeah, let's just chit chat, whatever. Yeah.
Yeah. Other questions? Yeah.
Wow, very quiet. You know, I actually sneak out like during this presentation to go to other sessions. We are the one with least people.
Oh, really? I see.
What the name is confusing. The name people. What is this section?
Yeah, because it's a mix of things, right? I mean, that's why maybe people were going to a specific session. With Potpourri is just a mix. But pretty interesting work. I mean, you have given a lot of practical tips on this, and the document. I just want to make a couple of comments. Documentation is definitely one of the issues, right? I mean, they say that to build a 787, the weight of the documentation weighs more than the weight of the plane, right? I mean, otherwise you can't build a 787. So I mean, that is definitely one of the challenges, right? I mean, the lack of documentation and also the magic bit that you were saying. I mean, this invariably magic bit is a problem, right? Oftentimes people do that, and yeah, it is. That's one of the elusive bugs to catch.
Yeah, it is, and it's everywhere. Like everyone I talk to, everyone use magic bit.
So I've got another question. We do some fancy way to use a System C model of the analog to run emulation for the big digital piece that has to talk to the analog.
Wow.
Do you guys have analog in your system at all, or?
Well, our emulation platform is pure digital. We have analog in the
emulation platform itself is pure digital. I'm talking about the overall system that you have to write the software for.
Yes, of course, it has, but it's not my department. It's the mixed signal guys. Like, so I'm in a digital world. Every simulation you might work is clean. That's why I said if I cannot reproduce an emulation, it's not my problem. It's someone else's problem.
Okay, yeah, we don't have time. We don't have time to do simulation for all of the stuff, especially for software development. Yep. We don't have time to do simulation to do the software development to work with this stuff. So we have to have an emulation solution for the for the analog piece, right?
Well, we use test chip. We have a test chip that has a real analog in it, and then the mixed signal guy play with it. It takes about like
if you can put that in the emulator. Do you have that in the emulator so they can test their software with that piece?
I don't know. The analog IP. Well,
because you have to write software that controls that analog. Your software system has to control the whole thing, right?
Actually, okay. In our case, it's a bit different. The analog has their own CPU, so the big CPU doesn't deal with the analog CPU. So the analog CPU is kind of living in their own world.
But they have to test their software.
Well, it's their problem. It's not my problem.
I see.
I deal with the big data path logic, those kind of things. So I'm not sure what they do, honestly. It's different department.
I see. Okay.
Yeah, but I know how we deal with it in terms of software firmware. We actually use test chip. I know we tape a test chip like half a year.
Yeah, our system, we have a lot of stuff that is firmware. So we have firmware in our CPU to do some of the analog control. Plus, we have software that sits on top of the whole system that runs on the, we have firmware in the engine, software that sits on the CPU that controls the engine, plus the analog piece. And so we have to do both of those parts.
Wow,
to be
that's hard.
Before we get the verification right. And of course, one of the problems is the emulated analog design doesn't actually use all of the registers in the analog block.
No.
But so this This is one
How
of
do you
the
solve it?
reasons
Just
why
curious. I have a paper on it last time. That's what my paper is on. The one that I won the best paper award. How to solve that problem?
Yeah, that may be why I voted for it.
Oh, thanks. Yeah. Okay. That's a new question.
I think there's a new question. Yeah.
Do you have any DPI application interacting with the RTL running in your emulator? My understanding is that a lot of work done with analog model in simulation has that analog stuff model via DPI applications, and that some emulators support linking DPI at a performance cost. Okay, long story short, actually I'll start with using DPI for code simulation with like software and simulator before we have emulator many years ago. After I got the emulator, I totally ditched the approach, and I literally, because we're using Palladium, DPI is slow, so I don't use DPI at all. I just stick with the I don't even use the simulation based transaction AVIP. We actually just use a pure real PCIe to connect to the emulation to make it run fast. So we actually just plug in a PCIe as a real PCIe controlled by a host in the emulator to minimize the slowdown of the cost. I actually did some ROI on this kind of thing. That's many years ago. Like when I also made the very first Palladium paper on DVCon as well. In order to justify the cost of a $2 million Palladium, you cannot have like 400x or 500x speed up using the DPI. You need to have at least 4,000-5,000 speed up. Otherwise, the money you just better spend on buying more server farm to make it run faster. So it's kind of, yes, you can do it use DPI. It will come at performance cost, but it doesn't make economical sense if you calculate the ROI. Oh, my son had just come in.
Regarding Jonathan's question, sometimes we include testing the analog model side by side with the RTL by having the magic numbers be in a DPI application that we link with the simulation. So I saw for a minute a way for the software to run on the simulated analog hardware in emulation, but it comes with that DPI performance cost to include that model. What? And
how do you justify ROI then? Like,
okay. I mean, it would be a very accurate test platform, but it is probably too expensive for what it is. I definitely would not want to pay that performance cost on every emulation run.
Yeah.
My emulation case, we have to simulate the signal path with a fairly high speed. And so our solution is, we have to simulate the signal path plus impairments of the signal path, right? For the digital system to do the compensation for impairment, right? Because that's what the digital system is supposed to do. So in our case, we have a system C model that we use an HLS process to get something we can emulate.
Oh, that's neat.
Right, rather than try to use the actual net list of the analog or anything like that.
It will take forever.
Yeah, yeah. So I would say the DPI. I was typing up an answer, but we actually use the PLI for analog modeling, but it's not. There's no way we could ever take that anywhere near an emulator. Now, maybe if you were doing something like a power management unit for a bigger CPU, that wouldn't need as many cycles, and maybe you could push that into the simulation. while other stuff is in the emulator. You know, I know one of the vendors today in the vendor session was talking about run the sim up to a certain point and then push it into emulator. Right? Or then, you know, switch it back, you know, run it in emulator and then switch this block back to RTL.
It works. It
in
actually
the
works.
middle of the simulation.
It works. It works. Palladium works like a charm. I do it all the time.
Yeah. Hey, we are almost up the hour, so maybe it's a good time to, if you want to continue the discussion, feel free to do so. I think through the virtual side, I think you could. Horace, you know, I'd like to thank you for, you know, providing a lot of very interesting tips, you know, very practical. I just want to make, you know, one comment. They say that when NASA sent the Mars rover, they didn't want to find the bugs either in the hardware or in the software, but they wanted to find the bugs on the Martian surface, you know, not anywhere else. Okay, so it was a, you know, it was a perfect mission. So thank you very much. You know, it was a great presentation. I would like to thank, you know, all our presenters and the authors and the audience for attending this session. I would also like to thank the Conference Catalyst workers for, you know, helping with the video and everything. So have a great day. Thank you.
Bye-bye.
Bye.